So we're going to look at proving things, how to prove things are subgroups, and the method is going to be called the two-step subgroup test. What does the two-step subgroup test say? It says a non-empty set H, a non-empty set H of a group G is a subgroup of G provided two things happen. Number one, if A and B are an H, then A times B is an H. And number two, if A is an H, then A inverse is an H. So basically there's a three-step process of showing something's a subgroup. First you have to show H is non-empty. Then you have to show closure. And then you have to show for every element in H, there's an inverse in H. So it's really a three-step process, but they call it the two-step subgroup test. Let's actually prove this. Tells you that H is a subgroup. Okay, we're going to prove this theorem. So we're going to prove that this implies that H is a subgroup of G. So suppose H is a non-empty subset of G that satisfies properties 1 and 2. In other words, closure under the star operation in the presence of inverses for every element in H. So what we have to do, we have to prove the four axioms of a group, right? We want to prove basically H is a group within G. So we already know it's non-empty, right? And we have it's a subset. So we have to prove the four axioms. So one, we have to show closure under addition. So note, by big one, H is closed under the operation. I'll just call it star. Okay, so you have closure under the operation. So 2. You have associativity. Why do you have associativity? Note, H is a subset of G, so star, I should say since star is associative on G, then star is associative on H. Right, if the operation is associative for all the elements of G, it has to be associative for all the elements of H because H is contained in G. Okay. 3. This is the one usually we're going to do 3. 3 is about the identity. We're going to do that last. So we're actually going to do 4 next, which is about inverses. So note, for each element of H, there's an inverse in H. And this is by 2 tells us this, right? Capital 2 tells us that. Now 3 is the most difficult one. You have to show the identity. You have to show that the identity is in H. So we know H is non-empty. That's assumed here. So since H is non-empty, then there exists an element, let's call it A, in H, some A in H. But by capital 2, H as well. Now, we know that the identity is equal to A starred with A inverse. That's always true. But if we use property 1, we have closure. So A star A inverse is an H. This is by 1, just by closure. So therefore, the identity is an H, if you just follow that line through. So we have properties 1, 2, 4, and 3 of a group. So therefore, this is just the definition of a group. Therefore, H is a group within G. Hence, H is a subgroup of G. So that is proving the two-step subgroup test. Now we want to use that. We want to prove some things or subgroups. Let's go into Theorem 7.3. Before I do Theorem 7.3, let me give a definition. So we defined the center of a ring when we studied rings. We're going to define the center of the group. It's practically the same thing. So a definition, let G be a group the center of G, that's what we're defining, denoted Z of G, is defined to be, so I don't know if you remember this definition, it's everything that commutes in the group, those elements that commute in the group. So it's the set of all elements in G, so all A and G, such that A little g equals G little a for all G and G. So this is a set of elements that commutes with all the other elements in the group. So this is called the center. So it's all those elements that commute with all the other elements. So we want to prove that this is actually a subgroup of G. So Theorem 7.13, the center of G is a subgroup of G. Proof. So we're going to use the two-step subgroup test. So first of all, I'm just going to write down what the center of G is, just so we can see what it looks like, the definition. So we have it above. I'm going to write it down again, though. So I'm going to say let the center of G be the set of all A and G, all the elements in G such that AG equals GA for all elements G and G. Okay, I'm just having that for reference so I can see what this is defined to be. Okay, so you have to show, first of all, let's note the center of G is a subset of G. Why is that? If you think about it, all your elements A are coming from G. So the center of G is living in G. Now you got to declare it's non-empty. How do you show it's non-empty? How do you show there's an element in there? Oftentimes you want to show that the identity element is in there. In this case, it's easy to see the identity is in there. We're going to show the identity's in there. So, oops. Let's say just say note EG, right? E is the identity equals G equals GE. This is for all G and G. So note that the identity commutes with every element of G. So thus, the identity is in the center. The identity is in the center because it commutes with every element of G. So the center of G is non-empty. Okay, now we want to show the first real step of the subgroup test. We want to show closure under addition. So I'm going to take two arbitrary elements. Let A and B both be in the center. So we show closure under the operation. We'll just call it star. Oh, what does it mean if A is in the center and B is in the center? That means what? AG equals GA. And if B is in the center, BG equals GB. This is for all G and G. Okay, I should have written that. So I'm unraveling the definition of A being in the center and B being in the center. Okay, so I want to show that A times B is in the center. So let's take A times B, and let's multiply it by G. And here our goal, kind of thinking, so do a little scratch work. You want to get AB times G equals, so at the end of this, I'm doing scratch work in yellow. You want to get G is equal to AB, right? You want to be able to show that AB commutes with G. So how do we get there? So first of all, red is my actual work. I'm going to reassociate. I'm going to get A and then BG in parentheses. Now we know that B and G commute, right? Because B is in the center. So we're going to have A, and then we're going to switch the G and the B. And then we can reassociate A next to G in parentheses. And then we can flip those because we know AG equals GA because A was in the center. So this is going to be GA. And then G, and then reassociate the parentheses AB. And that's what we wanted, right? We wanted AB, G equals GAB. So thus, AB is in the center of G. Number two, we want to show each element of the center has an inverse in the center. So right now we have A is in the center and AG would be equal to GA for all G and G. Now let's look at A inverse. We know A inverse is an element of G. We want to show it's in the center. So let's look at A inverse G. Now what do we want to get? So scratch work on the side in yellow. We want A inverse G equals G A inverse. That's the goal. So how do we do that? How do we do that? We have to do some tricks here. So what I'm going to do, I am going to open up. Probably what I want to do, I probably want to multiply by E here on the right. That doesn't change anything. And then I can rename this E here on the right. I can rename it A inverse times A. Is that what I want to do? No, I want to do A inverse. Okay. I don't want to do A inverse A. I want to do A inverse. Okay. Okay, now what I'm going to do, I'm going to reassociate. I'm going to put the G and the A next to each other. The A inverse on the outside. I'm just reassociating. Now we know that A and G commute because A is in the center. We're going to have A inverse. We're going to have A G, and then A inverse. And now I can reassociate. I get A inverse A in parentheses together. I got G A inverse out there. Now A inverse A is going to give me the identity. So I'm going to have the identity G A inverse. In other words, I'm going to have G A inverse. And that's what we wanted to show, right? We wanted to show that A inverse G is G A inverse. This is assuming for all G's, right? For every G. I should say for all G and G. I should have said that last time. For all G and G. So because A inverse commutes with every element G in the group, then that means A inverse is in the center G. So we've proven closure under the operation. We've proven inverses are in the center. So therefore, by the two-step subgroup test, by the two-step subgroup test, the center of G is a subgroup of G. Okay. Throw another definition out there. Now let's say you have a group G. Let G be a group. And let's say you take a particular element A of G, and I put these angular brackets around A. This is defined to be the set of all A to the n powers, such that n is an integer. So it could be a positive integer, it could be a negative integer, it could be 0, not necessarily positive. So this is the set of elements generated by A. That's the way we define it. The set of all elements generated by A. So all the powers of A, positive powers, the 0th power, which is the identity, and then negative powers. So we're going to actually prove that this is a group, this set generated by A as a group. That's what we want to prove. So this is Theorem 7.14. If G is a group, and A is an element of G, then angular brackets A, which is a set of all powers of A, set of all powers of A, or the set of all elements generated by A, is a subgroup of G. Okay, so let's prove this. So proof. So let A be an element of a group G. So first we got to show, let's just note first. Note that this guy is a subset of G. Why is angular brackets A a subset of G? So it's powers of A, right? Powers of A. So when you take powers of A, and the A is in G, then powers of A are just going to end up back in G. So powers of A just end up back in G. We also got to show it's non-empty. How do you show it's non-empty? Well, Note that A equals a to the 1 power. A to the 1 power is simply a power of A, so that's in angular brackets A, right? So thus, angular brackets A is not empty. Okay. So we want to end up showing closure and inverses exist. So let's take two elements, x and y, in the set generated by A, or angular brackets A. That means x is equal to a to some power, and y is equal to a to some power. These are going to be integers. M and n are going to be integers. They don't have to be positive. They could be negative. Could be 0. So we're going to show closure under multiplication. We show angular brackets A is closed under the operation. We'll just call it star. We don't know what the operation is, so we use a generic star. Okay, so what we're going to do, we're going to take x, start with y. So that's going to be what? A to the m. Start with a to the n. And we know the properties for elements of groups involves adding the power, so you're going to a to the m plus n. Now a to the m plus n is just a power of a, so this is an element of angular brackets A. Okay, so we have closure, right? xy is in angular brackets A. Now we have to show inverses. We show each element of angular brackets A has an inverse in A. Okay, so we assume that x is an A, so x equals a to the m power. We already have that. So let's consider x inverse. What would x inverse be? X inverse would be a to the m to the minus 1. And from some of our work that we've done in, I think, section 7.2, properties of basic properties of groups, this is the same thing. So a to the m's inverse would be a to the minus m. And that's a power of a, right? That's a power of a. So this is in angular brackets A. So x inverse is in angular brackets A, so we have inverses. So by the two-step subgroup test, angular brackets A, that's the subgroup generated by A, is a subgroup of G, and of group. So here's a definition that follows up to that. Special set generated by A. A group, no, let me say it this way. If a group G can be written in the form angular brackets A, then we say that G is cyclic. Cyclic. Some people say cyclic, but it's cyclic is the most common pronunciation I've heard. So we call G the cyclic group generated by A. Let me just give you an example of this. So here's an example. Let's talk about U10. That's a multiplicative group. So these are what the units of Z10. So you're talking about those equivalence classes that are relatively prime. Their integer part is relatively prime to 10. So you're going to have 1 bar, not 2 bar, 3 bar, not 4 bar, not 5 bar, not 6 bar, 7 bar, not 8 bar, 9 bar. So it has 4 elements. So it turns out that U10 is equal to angular brackets 3 bar. So what do I mean by that? So let's think about 3 bar. 3 bar to the 1 power is 3 bar. Right? So I'm writing 3 bar down here with the angular bracket. So I got one of my elements is 3 bar in here. 3 bar to the second power is 9 bar. 3 bar to the third power is 27 bar. But reduce that modulo 10, and you're back to 7 bar. So 7 bar. And 3 bar to the fourth power is, that's going to be what? 7 bar times another 3 bars. It's going to be 21 bar. But reduce that modulo 10, you're back to 1 bar. So 1 bar. So 3 bar, 1, 3, 9, 7 is the same thing as U10. Right? These are the same. So that means U10 is equal to 3 bar. So because U10 can be generated by a single element, it's said to be cyclic, right? It's cyclic because 3 bar cycles you through all, the powers of 3 bar cycle you through all the elements of U10. So U10 is a cyclic group generated by a single element, 3 bar. That's what it means to be cyclic. You're generated by a single element. Okay, what else do I want to say here? Let me give you some additive cyclic groups. That was a multiplicative cyclic group, an additive cyclic group. Zn. So under addition, Zn is an additive group. What are the elements? 0 bar, right? 1 bar, 2 bar, 3 bar, so on and so forth, all the way up to n minus 1 bar. And then n bar is back to 0 bar. So you can actually write this actually as n times, well, let me say k times 1 bar. Let me write it that way. So rather than using exponents, okay, I can't get to, there it goes. Rather than using exponents when you're doing additive, so with multiplicative notation you use exponents, right? We had exponents of like 1, 2, 3, and 4. When you're doing additive notation, you put the number out in front. So you're going to have let's say a k out in front, where k is a integer here. Let's think about it. So you got 1 bar. I got 1 copy of 1 bar is 1 bar. I got 2 times 1 bar. That's going to be 2 bar. I got 3 times 1 bar. That's going to be 3 bar. And you just keep going until you get to n minus 1. Right, these are your k's. K equals 1, k equals 2, k equals n minus 1. You multiply that by 1 bar and you get n minus 1 bar. So we would say this is generated by 1 bar, right? 1 bar is the generator. You just take, rather than powers of 1 bar, you're taking multiples of 1 bar. When you're doing additive groups, you take multiples rather than powers. Yeah. So Zn is cyclic and is generated by 1 bar. Here's another famous group, the integers under addition. What do you have? You have 0, plus or minus 1, plus or minus 2, plus or minus 3, so on and so forth, the integers. You think about the integers. There's a single element that generates them. It's the number 1. You just put a k out in front of that. Any integer k. So think about it. So how do I get, so let's take the number 1. How do I get the number 0? What do I have to multiply 1 by? Well, I multiply by 0, right? 0 times 1 gives me 0. Then let's say I want to get the number 1. What do I multiply by? 1. Or let's say I want to get either positive 1 or negative 1, plus or minus 1. Then I multiply by either plus or minus 1. Let's say I want to get, what do I multiply 1 by to get plus or minus 2? Well, I multiply by plus or minus 2, and so on and so forth. Okay, so that means the integers are generated by 1. You just take not powers of 1, but multiples of 1 in this case. So the integers, the set of integers is cyclic as an additive group and is generated by the number 1. Okay, so famous cyclic groups.